Okay, so now we're going to be wrapping up Fourier series and Fourier transforms by talking about some application of Fourier transforms. First, we have Parseval's theorem. Now, Parseval's theorem essentially states that we can find the power of a time function by actually using the Fourier transform of the time function. So we can always find the power of a continuous signal being given as the integral from negative infinity to infinity of some kind of time function squared dt. However, in general, this could be very tedious and quite possibly very difficult. So this one, we generally say difficult. However, in the frequency domain, we can actually find the power using the magnitude of it. So we have the integral from negative infinity to infinity of the absolute value of x of f squared df. Now, to kind of show you the difference, it's like asking what is maybe the sine. Suppose we have sine of f naught t. We can, when it comes to squaring this, we have to do a double angle, or we have to do an expansion on it. Whereas in, or actually the best case would just be talking about cosine instead. So let's talk about cosine instead. In cosine, we have to kind of square this, expand it, and then integrate it from negative infinity to infinity. A little too difficult. Whereas for this, we have 1/2 delta f minus f naught plus delta f plus f naught. And the integral of a delta function is just whatever value it is of that time function acting on at f naught in both the plus minus of f naught, and then multiply by 1/2. So notice the difference. This one is easier to evaluate as an integral compared to this. And that's the idea of Parseval's theorem, just that we can assess the power of a signal by looking at it in the frequency domain compared to the time domain. Now, what about modulation theorem? Modulation theorem tells us that for any time function, if we have cosine of 2 pi fct, and fc is usually denoted as center frequency, we can actually find its Fourier transform as 1/2 x of f minus f naught plus x of f plus f naught. Graphically, it looks something like this. So suppose this was maybe a cosine function. Then in this situation, the frequency domain, or at least the magnitude of it, looks something like this. For in the event x of t is equal to some cosine of 2 pi f naught t, where, actually, just to kind of keep it consistent with analog communication, fm. So this means that we have fm plus fc, and then the negative version of this. Or graphically, it looks something like so, like this. So we have two kind of signals represented both in the real and time domain. For in the event, we have x of t equal to cosine 2 pi fm t. And then we multiply that again with cosine of 2 pi fct to apply modulation theorem. This one is f not fc plus fm, and then fc minus fm. And then on the other side, we have negative FC plus FM and negative FC minus FM. So that is one more application in analog communication systems when we're talking about modulation. And actually, on the topic of modulation, that is the whole essence of AM and FM modulation process, where we essentially are using Fourier transforms and using cosine to basically transmit a signal from a transmitter to a receiver. Now, I could go into detail about the whole process, but I'll show you briefly just what I mean. You have some kind of signal, let's call it S of t, and you have to multiply this to some kind of center frequency. So we use this symbol. This is a multiplication symbol, and then we multiply this to an oscillator given by 2 pi fct. And from here, we have Sm of t, which is our signal with a carrier frequency. And this is what we send over the transmitter. Now, to the transmitter, and we have to demodulate it by multiplying it to a local oscillator of the same frequency, cosine of 2 pi fct. And then we have to pass it through a low pass filter with a window of FM to minus FM. And from there, we're able to get our transmitted signal. That is, in essence, the AM process. Now, the FM process is a little more complicated, but it follows a similar idea. And for this specific situation, this is actually what's called AM double sideband, or DSB, suppressed carrier. We're essentially using a crystal oscillator to kind of carry our signal through. And so our center of frequency is really large sometimes. So maybe sometimes greater than FM. And from there, we're able to transmit. This is the most basic process of modulation. Now, there are some issues with this, and for the viewer, whenever you take analog communication systems, you understand that the limitation of AM/DSB/SC is the whole issue of these two oscillators. However, I will not discuss about this. Simply, this is as good as we'll have it. So, hopefully you've learned something about Fourier transforms, and that you understand that the important applications of Fourier transforms are within the realm of communication systems. I also hope you understand that Fourier and Laplace go hand in hand when we kind of discuss about them as a general analysis technique. Okay, thank you.